So this is the last lecture chunk here for lecture 2. This is kind of just an additional piece to go over kind of this final example that's in your notes. We'll go over it in class, but I thought what I'd do is provide a video snippet here on filling out the 5-year return interval and basically going over everything that we just went over in the other 3 lecture chunks, but doing it applied to this set of data that you can see right here. So we're given some data, which is the annual maximum 10-minute rainfall in inches at Chicago. So what that means is we found for any given year what the maximum amount of rainfall that occurred in 10 minutes was. So, let's say if we look here, it's a 19, it's kind of a funny way that these things are set up. This is 1913. So in 1913, about the highest 10-minute rainfall in a period throughout 1913 was about half an inch. That's that was the highest rate. And over here we can see in 1936 almost 1.11 inches, just more than an inch fell within 10 minutes. So that was the highest 10-minute rainfall for that year. So this is called the annual maximum series. And what we want to do is we want to look and we want to find the 5, 10, and 50-year 10-minute rainfall magnitudes. And we can confirm our values using this concept that we'll call relative probability. So what we're going to do is we're going to fill in at least the boxes for the 5-year events, and then I'll leave it up to you if you want to go on and we'll go through doing this in Excel as well to fill in the 10 and 50-year events, because it'll go a little faster if you do it that way. Okay, so some of the most important pieces to kind of figure out here in the very beginning are we just want to get the mean. So I'm going to give that to you. I went into Excel and I took these numbers and I calculated out what the mean is. So it's about 0.65 inches. I figured out what the standard deviation was. It's about 0.18 inches, and you could have figured that out by basically subtracting, differencing each value from the mean, squaring it, going through and calculating the variance. You could have done that by hand as well. It would have taken a while, but in this case, I just did it using Excel. I counted that there were 35 total events, right? And then I used basically what we know about the alpha and beta parameters for the gamma distribution. You'll see why these become useful if we were to solve this in Excel. And I took the mean squared over the standard deviation squared. That's what the alpha parameter is, and I got 13.39. And then I found the beta parameter, which is the standard deviation squared divided by the mean, and that's 0.048. So let's now go ahead and we're going to calculate the 5-year, right? The 5-year return interval normal, basically estimate of rain given this data using a normal distribution, using a gamma distribution, and then just calculating it by hand given the data that we see here, right? Okay, so let's start out with the normal distribution. We know that what we're looking for here is a 5-year return interval event, right? So we're looking for the event that happens on average once every 5 years. So that's basically an 80th percentile event. What we're essentially saying is we're trying to find the rain amount where 80% of the distribution is less than that amount, right? And if you recall, we have our table from the lecture notes here, and it's, you can get them in the book or online. And what we're looking for is a cumulative probability of the normal distribution that's somewhere around 0.8. And so in this case, we see that it's a z-value between 0.5 and 1. Now, we don't know exactly, what you could do is do a little interpolation routine to figure out exactly what it is. You could put it in a calculator, you could look it up on a more detailed table, right? What I did is I just went online and I basically found that the exact value, we'll see in a second, is about 0.75 or something like that, right? But we can tell, let's say on an exam, that it's somewhere between 0.5 and 1, so you might just make a guess and say, I don't know, let's see, we've got 0.7 and 0.84, it's 0.77, right? And that would be kind of your guess at what 0.8 is for z. Okay, so again, what do we have? We've got 80%, right, of our values are less than this one we're trying to find. The exact z-value in this case is 0.7881 if you were to look it up in a textbook or online in a very detailed table. And now we just use the equation that we went over in the second lecture chunk, right? We take the mean of our data, right, our x bar, and we add to it the standard deviation times this z value, right? And so what we should get out then is our answer. It's saying if we use the normal distribution to model this data, right, and we give the normal distribution this mean and this standard deviation, what our normal distribution model says is the 80th percentile type event, it's 0.792 inches. Okay, so how accurate is that? And that's a good question, right? How accurate, you know, is it okay to apply the normal distribution to this data, right? That's the question. Well, let's check. So one thing we could do to check is we could just take our observed data and rank it and find something that's close to the 80th percentile. That's what we would call the relative probability. So let's look here. Basically, we know we want to find some value at the 80th percentile, so how do we do that? Well, what we know is that basically 80% of 35 values is 28. So really we're looking for a value that's, if we took all these values and ranked them from high to low, the value that would be at slot 7, or if we were ranking them from low to high at slot 27, right? So we're looking at basically the 7th value or the 8th value from the top. That would be a value that corresponds to being greater than 80% of all the other observed data. So literally what I'm going to do is I'm just going to mark them as I see them. So here I see this one's 1.11, so that's my highest. And then up here I've got 0.96, 0.94, and 0.92. Over here I've got 0.88 and 0.80. So I've got 1, 2, 3, 4, 5, 6. So it looks like my next value, 7, is right here. So my, the value, the 80th percentile value, or the one that's 7th from the top, is 0.8, right? And so I'm going to stick that in here, and that would be my relative probability. And just, kind of judging between these two numbers, right, it looks like they're pretty close. So that's good. So the normal distribution made a pretty decent approximation of what we see in our observed data. So now the last question is, what about this gamma distribution? How do we do that? Okay, well, apparently my animations are out of order, but here's the answer, and we're going to see that it's actually pretty close to the relative probability as well. So let's look. The first thing we want to do is we want to calculate the skew coefficient. Again, right, C sub s. And we know that that's defined as 2 divided by the square root of alpha, right? And in this case, we said alpha is 13.39, right? So we just take 2 divided by the square root of that value, and we get a skew coefficient of 0.547. Okay, good. And from our book, if we go to our table on page 195, right, we should be able to look up a k value such that we have a C sub s, or a skew value, of 0.547, so that would be one of the columns. And then we would go across until we had a recurrence interval, right, in years of 5, right, or a percent chance, in this case of, 20% chance of happening in any given year. And if we were to go through and follow down the columns, if you were to go to page 195 and look down through the book, you would go all the way down to in between kind of 0.5 and 0.6, right? And then you would read across to column that had a recurrence interval of 5 years, and we'd find, in this case I just chose 0.808, but it would be, somewhere in between 0.808 and 0.8. So maybe, we'd be 0.804 if we wanted to be exact. Now all we have to do is take that and put it into our equation, just like we had in lecture chunk 3. We've got the mean, we've got the standard deviation times k, and it turns out that the gamma distribution, if we were to use that to model this set of data and look at what the 5-year return interval, or the 80th percentile probability, would be, we would see that it would be 0.795 inches. That's what it would return. Okay, so great. So there we go. Now that's how we do it by hand, right, using either our z table or our frequency factor table. What if we want to do something a little bit more sophisticated? Let's say we wanted to use a program like Excel. Well, we could complete this in Excel by basically using the function norm.inv, which means we're going to take an inverse of the normal distribution. We're going to give it a probability a mean and a standard deviation. And what it's going to return to us is a value. And that's different than what you would have learned in computer apps, where we use the function norm.dist, which we would take the normal distribution, and there we would give it an actual value, we would give it a mean and a standard deviation, and we would have it return to us a probability, right? So we can go both ways, and we'll spend a lot of time doing that in our homework and in the lab. But in this case, we would use this function norm.inverse. We would give it a probability, so in this case 0.8. We'd give it our mean, which we have here. We'd give it our standard deviation, which we have here. And we would find, if we put this into Excel, that it would return about 0.798. So that's pretty close to what we calculated by hand. Here, the difference is in the decimals, right? In one case, I've truncated some. In Excel, I haven't truncated any, so it's a little bit more exact. And it's actually a lot closer to our relative probability. Okay. How do we do it with the gamma distribution? Well, with the gamma distribution, we would give it the gamma inverse function. So we'd say equals gamma.inv, and we'd give it a probability, our alpha, and our beta values that we calculated here, right? Again, and all alpha is, right, it's just the mean squared divided by the standard deviation squared. So if you calculate this for any set of data, it's pretty trivial to get the alpha and the beta, which is just the standard deviation squared divided by the mean. So here we'd do the same thing, and we'd find that it would return something 0.791. Okay, and so lastly, what do we think? Why, how good of a fit is this? How do we know what how do we know how our data are distributed? What should we use the normal? Should we use the gamma? Which one's better? Well, we could, use a histogram, obviously, to help us figure out, how the data look, how they're distributed. But we could also plot the CDFs, the CDF of our observed data, and then the CDFs of our two model fits, our normal and gamma distribution fits, and see how well, over the whole range of probabilities, our models match. And we'll do that in lab with streamflow data, and it should be pretty interesting. Okay, so we'll see you in class, and the next lecture chunk 3, we'll start kind of getting more into away from the statistics and more into the hydrological side of things.